Time to talk about pH. pH is going to be a very important concept when we're talking about acids and bases. This is going to be what tells us how acidic is that acid, how basic is that base. It's going to provide the measurement tool for us to understand this. This is probably the most complicated part from this chapter, so these 10 pages here may be invaluable for you to look at. So the first thing you've really got to understand with this is we've talked about how things ionize when we throw them into water, but it turns out that water actually goes through a process called self-ionization. At a very, very low level, a water is going to react with another water in order to form hydroxide and a hydronium. You can treat hydronium, it's really just the same thing as when we draw a hydrogen ion by itself in a solution. It's not technically a hydrogen ion by itself, it's a hydronium. You can draw it as a hydrogen ion, that's just fine, but it's actually this, hydronium. You may want to write down that word if you don't already have it in your notes. And you'll notice this is just acting like an acid-base reaction because a hydrogen moved from one thing to another. So this happens at a very low level. In fact, that level of autoionization that's occurring, the amount of hydroxides and the amount of hydroniums are equal, and that concentration is 1.0 times 10 to the negative 7th molar. 1.0 times 10 to the negative 7th molar of this, 1.0 times 10 to the negative 7th molar of this, in pure water at 25 degrees C. 25 degrees C is approximately room temperature water. Now, that is considered neutral, a neutral solution. And it turns out that the product of both of those multiplied together, the hydrogen ion concentration and the hydroxide ion concentration, is something called Kw. Kw for water at room temperature will always be 1.0 times 10 to the negative 14th. This is important. It's a number I'm not going to make you memorize because I don't make you memorize very many things, but this number is not going to change when we're at room temperature. And just to make it simple, I'll go ahead and tell you all the acid bases that we'll be doing are going to be at this 25 degrees C. This times this will always equal this number, even if it's not neutral. And that's going to be very important to what we're going to see next. So, for acids and bases, we can change these concentrations. If we have more protons, more hydrogen ions, more hydroniums than hydroxides, that's an acidic solution. How about basic? What would make something basic? More hydroxides than hydrogens gives us basic. And a neutral solution will have, if you answered equal amounts, that's exactly correct. So, remember what I said, that the hydrogen times hydroxide ion concentration is always going to need to be that 1.0 times 10 to the negative 14th. So what if I asked you to do a quick little problem and tell me the concentration of hydrogen ions and hydroxide ions in a 1 molar solution of hydrochloric acid? Go ahead and try that, hit pause, and then let's resume and take a look at it together. And we're back. So we've got 1 molar hydrochloric acid. Hydrochloric acid, as you may remember, is a strong acid. And since it's a strong acid, that means how much hydrogen ion are we going to be producing? If we've got 1 molar hydrochloric acid, we're going to be producing 1 molar hydrogen ions. So that's our concentration of hydrogen ion. These brackets here mean concentration. I can't remember off the top of my head right now whether we've said that before or not. But what about the hydroxide? What about the hydroxide ion concentration? What is that going to be? Well, what's the relationship between the hydrogen concentration and the hydroxide concentration? Well, we know if it's at room temperature, which is what it's going to be here, that number is always equal to that value, Kw, the dissociation constant of water. You don't need to know that, you can just call it Kw, which is, if you'll remember, 1.0 times 10 to the negative 14th. Again, that number I will give you. Since it's 1.0 times 10 to the negative 14th, we can set this up like an algebra problem. Which of these things do we know? We know this one here. We know this one here. We don't know this one. So let's set that up that way. 1.0 times 10 to the negative 14th, that's our value for Kw, is going to equal the hydrogen ion concentration, which is 1, times the hydroxide ion concentration, which we don't know, which is X. Hey, this works out very nicely, because anything divided by 1 is itself, which means our hydroxide ion concentration is 1.0 times 10 to the negative 14th. So, if we know either the concentration of hydrogens, hydroniums, or hydroxides, we can calculate the other one, because Kw will always be the same thing. Now, the numbers we're going to be working with for concentrations are often going to be very small. Do you remember what that concentration for those hydroxides just was? 1.0 times 10 to the negative 14th. This is a very small number. So as we saw in class, a good way that we can express a number that's either really big or really small is in terms of logarithms. Since the numbers are very small, we'll use logarithms. Logarithms, you'll remember, express things as a whole number value rather than as a power of 10. So here's what we're going to do. pH gives us a measurement of the concentration of hydrogen in terms of log. You're going to take your concentration of hydrogen, apply a logarithmic function to it. If you're using a scientific calculator, you'll put in the number first and then hit log. If you're using your graphing calculator, you'll do log and then the number. And then we're going to take the opposite of it. So, again, the steps to that: find the concentration of the hydrogen ions, use the log button on the calculator, and then make it positive. That's what this little piece is going to do here. Because if you go ahead and punch into your calculator right now, 1 times 10 to the negative 14th, you're going to come up with a negative, and we're not going to use negatives on our pH scale. Okay, so let's consider pH just a little bit more before moving on. Now, what number value would we use on the pH scale for neutral pH? Well, what is the hydrogen ion concentration of a neutral solution? You can look back in these notes a little bit if you need to, but what you'll see is that it's 1.0 times 10 to the negative 7th. So go ahead and enter that into your calculator. Take the log of 1.0 times 10 to the negative 7th. You'll get a negative 7. Remember, we've got to make that positive, and so we'll get 7. Neutral pH at room temperature is 7. If the pH is less than 7, we're going to have an acidic solution. If it's more than 7, we'll have a basic solution. Let's also try to think real quick. What is the highest possible value for pH? What is the largest number, the most basic number we can get for pH? And with a little bit of reasoning and a little bit of math, not that we need to derive it here, you will see that the most basic number we can get is a pH of 14. The pH scale won't go any higher than 14. So here's a little graph over here on this side. I like this one because it has a few pictures we can see here. Your screen might not show all the way up to 14 up here. I know mine does. But you can see that as we move down, things become more acidic. The pH goes lower. Battery acids, lemon juice, coffee, things like blood are very close to neutral, although slightly basic. And we get more basic as we move up. Now, we're going to be dealing a lot with pH in the rest of this chapter. There's two main ways to measure pH. We could use an indicator. Indicators are a little bit trickier to use for reasons that we'll discuss in class next time. My favorite tool for measuring pH is a pH probe such as this. You know how much I love the LabQuest, and this plugs right into the LabQuest and will give us a nice pH reading with no guessing involved. One more thing to talk about, and then we'll be done today. A related concept to pH called pOH. Now, if pH is the negative log of hydrogen ion concentration, then pOH, how would you find that? What would pOH be equal to? Right, the negative log of the hydroxide concentration. So it's a reciprocal inverse sort of relationship here. So what if you took the pH of a solution plus the pOH of a solution? What number do you think you would get? I'll give you a hint. It's a number we've seen several times in this slideshow. See if you can get it. And it is 14. pH plus pOH will always equal 14. This is going to become a very simple way to come up with our, to convert between hydrogen ion concentration and hydroxide ion concentration. The rules here will become reversed. In pOH scale, the low numbers are basic, not acidic, and the high numbers are acidic, not basic. We won't use pOH as often as pH, but it will provide an easy way to go from one to the other if you need to do that. That's it for tonight. Do try to read that section in the book and try some of the practice problems. It'll do you good.